do you want to say a few words, or I start introduction? You good to go? Okay, so it's a pleasure to introduce Team Kusky. Team is working on plate tectonics and applying it to early Earth evolution, especially to Archean. Team got his bachelor and master degree at State University of New York at Albany, I guess probably working with Bill Keats. And when he did his PhD at Johns Hopkins University and graduated in 1990, after it, he did a postdoc at University of California, Santa Barbara, and then had various positions at University of Houston, Boston University, until he ended with tenure track position in St. Louis University, where he worked from 2000 to 2009. In 2009, Team moved to various positions in China University of Geosciences in Wuhan and Beijing, and worked with University of Chinese Academy of Sciences in Beijing. And he works through various Archean terrains in Australia, China, South Africa, Zimbabwe, and today he will present about his work on North China Craton. So with this, Team, it's all yours.
Okay. Thank you, Andre, and welcome, everybody. I will be talking about cratonic growth in an accretionary orogen from the North China Craton. And I'd like to start with just a quick summary of the main conclusions. I'll be talking about a 1,800 kilometer long orogenic belt mostly that has indicators, are key indicators of plate tectonics, including Alpine-style giant fold naps, for subduction initiation, passive margin that these naps were thrust over. And we found some eclogite facies, garnet peroxenite blocks, and even ultra-high pressure inclusions inside potiform chromatites. And then the conclusion will be is that the North China Craton grew by processes of accretion of arcs and other types of tectonic elements. Sorry. Oh, here we go. Okay, so in general, we can think about different ideas about the origin of cratons as two different general models. One is a top-down approach where we have subduction forming arcs and accretionary wedges and underplating of these slabs to form the subcontinental lithospheric mantle. And the other one is a bottom-up type of a model where we have plumes or something else underplating to the base of the pre-existing lithosphere and forming large igneous provinces that can do various things. If there's a thermal instability, they might drift back down into the lower crust or deeper. So we'll be looking at some of these different models. And the area that I'll be talking about for the next 45 or 55 minutes is this area, the North China Craton over here. Beijing's over here. Wuhan is down over here, south of the Dabi Sulu Orogen over here. So in general, this craton consists of an eastern block, which is a slightly older 2.56 to 2.9 billion-year-old Genesis baby, mostly, with some very old rocks as well, 3.5 or 3.8. Then we have this central orogenic belt, COB, which is the 1,800 kilometer long orogen, which is similar in size and shape to the Alps, shown over here, drawn at the same scale. Then we have Western Bloc and a few other different things, the Inner Mongolia North Hebei orogen, which were added to this growing cratonic collage in the Paleo-Proterozoic. So even the large-scale structure of sections of this orogen resemble the Alps. This is a cross-section I'll be showing for the first part of the talk. And in a general sense, it kind of resembles the Alpine system, where there's older continental basement like we have here and here, a passive margin and foreland basin sequence like we have here, and then these allochthons consisting of various oceanic units thrust on top of it. For those of you who are more familiar with North America, I've taken the outline of the North China Craton here, turned it upside down so that north is south, and we can compare it to the Appalachians, where we have older Cratonic basement over here. Then we have the Ordovician Tectonic allochthons, and then later Akkadian and Alleghenian overprints on top of that. So this is an example of an orogen that has multiple phases of deformation and tectonism, just like the central orogenic belt. So what I'll do is talk about a couple of the key areas along the boundary between this eastern block over here and the central orogenic belt. And I'll start with the Zanhuang Massif, which is right in the center of this boundary. And the boundary between these two different tectonic units goes right through here. This is the boundary right here. So this is the older basement of the eastern block. This, on a large scale, is a tectonic mélange belt intruded by 2.5 billion-year-old granites. And these are accreted TTG archetype rocks over here. So we spent some time with students. Some of their papers are shown right over here, making a very detailed cross-section through here. This was one of our first attempts where I identified two large-scale subhorizontal naps dipping around 10 or 15 degrees over here, being thrust towards the southeast over the older basement. And this is a passive margin type sequence deposited unconformably on the older basement. So here's a detailed profile with a lot of structural information. I'll show a little bit of the structure, but not too much. But we go from a melange at the top to black rock temple nap to a sheet folded nap down into more shear zones, and then to the basal décollement over here with a Buddha nap laying on top of it. And then there's this 2.56 or 2.58 to 2.50 passive margin type sequence down below it. So instead of showing the really detailed one all the time, I'll be showing this schematic profile where we extended the profile to the sky and down below the surface over here to make this detailed profile. So start with the melange at the top of the mountains. These consist of blocks of epidocites in a metapelitic matrix, all kinds of things. Some of these have clear pillow shapes that they used to be. And there's several different types of melanges. Some have P-lites and carbonates, some have the mafic and gabbroic type different sources over here. And you can see in some cases we have the epidocite altered cores still surrounded by the selvages, but deformed in the deformation involving the melange. So this was some mapping done by PhD student Junpeng Wang for his PhD. And it shows the detailed structure of the melange. But the important thing I want to show here is that the melange is cut by these different types of pegmatites and granites that cut across the fabrics, and they give an age of 2.5 for a maximum deformation. Then we look in more detail at these naps. The black rock temple nap at the top. This consists of picrites and bonanites folded together over here. And then there's a section missing because we didn't map it at this time. This is the basal Buddha nap. So this is the lower thrust over the foreland basin and passive margin type sequence over here. And it's folded around and then thrust over by the next naps over here. So the age constraints on these are that the tholeiites at the base of the Buddha nap, this is part of the Buddha nap over here, folded, yield ages of around 2.7, 2.699, 2.713 billion years. And we weren't able to get any zircons out of the picrite to bonanite series, but they are cut by these trunzomite dikes that have ages of 2.65 or 2.66 billion years old. So those are from these locations over here. So the naps are really quite deformed. They have three phases of deformation. The first one is locally transposed by the S2 deformation foliation here is the main nap-forming event that deforms these rocks. This is the sheath fold over here that looks like this. I don't want to talk too much about chemistry today, but these are the toluites in red and the picrites to bononites in blue, defining this picritic to bononitic series, like other subduction initiation sequences. The sheath folds, we mapped it going along the profiles on the road and hiking through the mountains as well. So you put together these different profiles and we're able to derive the shape of the sheath fold. It's about 10 kilometers long at a minimum and a couple kilometers wide in this direction over here. So these form by very high shear strains. And again, the ages are constrained by the cross-cutting dikes. Here's one of the pegmatites that cuts across, another pegmatite that cut right across these strong fabrics over here. And this is a whole pluton that cuts across the mélange belt over here. And another way to help with the dating is that in some cases, the basal shear zone has metamorphic zircons that grow in it over here. And many other places have metamorphic rims on the zircons that give ages of around 2.47 billion years. So we're pretty sure about the timing of this deformation and the southeast directed shearing. So then these rocks over here are thrust over this, we call this the frontal thrust sliver, which has a pretty thin foreland basin type sequence consisting of flysch, sandstone and shale interbedded. And then it goes down across another thrust fault into a passive margin type sequence that has carbonates at the top. These are marbles and sandstones and shales coming down to the base with the energy increasing as we go down to the base at nonconformity here. So these are some of the marbles. They're really quite beautiful. They're red and green and white. I'm not sure what that means in terms of oxidation, but very interesting to go through. And they don't have the early deformation that we see in the loxons and the naps. So another student for her undergraduate thesis, she looked at the sequence here, mapped it in detail from the basal unconformity to the carbonate at the top, and did a detrital zircon study and comes up with an age of 2.58 billion years at the base, and it's truncated by 2.50 billion-year-old thrusting at the top. So the unconformity is also deformed. It's folded and sheared, and it looks like this in the outcrop over here. And sitting on top of these older gneisses over here that have ages of around 2.7 to 2.56 billion year old. They're fairly complicated, but deformed previously. So one of the really interesting things we found and just published in EPSL last month is that this basal thrust not only takes 200 million year old rocks and thrusts them over 2.5 billion year old rocks, but there's an inverted metamorphic gradient associated with this big thrust fault, whereas the rocks at the top come from maybe 35 kilometers depth, and the top of the carbonate sequence never got buried to more than 15 kilometers over here, as shown by these pressure estimates. And in addition, the rocks on top show a counterclockwise decompressional PT path, where the ones in the autochthon are being heated up as the thrusting is going on. So we did some Peclet number analysis on this, and this is the thermal structure. So the rocks on top are being cooled. This is the cooling rate over here, while the rocks underneath are being heated during the thrusting. And in order to preserve this type of thermal structure, we calculated with Kurt Stewie and other people that this thrusting rate has to be around 3 centimeters per year. So putting all these things together, the age difference and the overall structure of this orogen looking like this, we just looked at this section right here, going from the naps to here. We didn't talk about the arc rocks. So we have about 178 million years between the subduction initiation sequence, the picrites to bononites, to the time of thrusting at 2.50 billion years. And if we, at that time, assumed a rate of 2 centimeters per year, we calculate that the amount of oceanic crust subducted in this system would be more than 3,500 kilometers. So again, this orogen has many characters that are similar to the Alps, but also different in many ways over here in terms of scale, in terms of structure. Here's a cross-section of the Alps drawn at enlarged vision over here. So it's very, very similar in terms of many things. So also, this is really important because this passive margin type sequence over here formed in an accretionary orogen. So we have this central orogenic belt right here, older orogens between accreted arcs and the eastern block over here. This is around 2.7 billion-year-old arcs that accreted. Then we have the passive margin developed on the backside of these accreted arcs, and the central orogenic belt is thrust on top of it. But this is happening at a very critical time in Earth history. This is around 2.50 billion years, and different models for the great oxidation event are showing oxygen whiffs starting at this time and really the beginning of the GOE. So we kind of relate this accretion of arcs on a large scale here and globally, perhaps in Kenorland, to formation of stable environments and creation of suitable environments for life to proliferate and oxygenate the atmosphere. So we're thinking about different correlations between different events right now. This is from our paper just published in Nature Com, correlating it with the GOE, different models and different tectonic events in the North China Craton and elsewhere. And other people are trying to think about the correlation of the GOE and the Loma-Gundy event. Okay, so I'm going a little fast because we have a lot of slides to talk about. So that was this area down here. I want to talk about this area in the north as well. This is called the Eastern Hebei province. And we found very interesting things here as well. So this is a map of the Eastern Hebei. We go again from the central orogenic belt here, consisting of metasedimentary gneisses in yellow and mafic, ultramafic belts, and the green color over here being thrust again to the southeast. And this is the older TTG and other units related to the earlier accretion of the arcs over here. And these rocks have a higher temperature geotherm, and some people say they're deformed into domes and basins, or from our mapping, we're suggesting that they are actually fold interference patterns formed during this deformation event. So I'll be looking with you at a couple different areas. One is this area over here called Shangyin, and the other one is down here by Zanhuang over here. This is the area where we documented the eclogite facies and morb type rocks. And this area has potiform chromites and the Harzbergite blocks associated with the melange and ophiolitic characteristics. And they're very interesting for their ultra high pressure characteristics. So just a quick summary. So this area is really good for having the ophiolitic fragments, no full complete ophiolites. Haired metamorphic belts are found down here initially, but they extend all the way up. For initiation subduction zones. And for now, we'll talk about the ultra high pressure stuff that is forming, again, in our interpretation, and this accretionary wedge at the front of this Wutai pooping arc system that was accreted at 2.5 billion years. So these rocks look like this. These aren't all from the same outcrop, but they're all from the same area. There's silicic shales, and there's units of pillow-like lavas over here. There's dike complexes, diabase dikes cutting gabbros and even ultramafic rocks, layered gabbros, Harzbergite cut by younger granites. And this is what the melange typically looks like. It's just blocks of different types of rocks and a metasedimentary, or in some cases, metavolcanic or amphibolitic type of matrix. So these are rocks in the field. We just took all the vegetation off this outcrop to map many of these dikes. You can see some of them here. Closer up, you can see the dikes cutting the coarser grained gabbro. So I put together this composite stratigraphic section going from the diffs, which are 2.54 billion years old, into pillow lavas. These are the ages over here, 2.505. You have to be careful in this area because there's many different mafic to granitic intrusions that run parallel to the igneous stratigraphy. And we have other types of ages, lutetium, hafnium, 25, 28 on the ultramafic rocks, and ruthenium, osmium on the chromite, all about the same, 2.55 to 2.505 billion years old. And then thrust on top of these older gneisses. So first, we'll look at this area, the Shenying area I pointed out on the last map, where we have a nice pyroxene hornblende plagioclase, kind of a mafic gneiss, but it has preserved within it these different tectonic blocks, mostly of gabbroic type rocks, but some of them are pillow lavas, some are gabbros, and even ultramafic rocks over here. But this one in particular is where we were able to document eclogite facies. So this is what it looks like here, slightly closer up. We have the garnet-rich zones, plagioclase-rich zones, and a layered gabbro complex. Here's the gneiss. And this is what the eclogite facies rock looks like. It's a garnet pyroxenite. It's not a true eclogite. It's not garnet anthracite. It's garnet pyroxene. But it did reach eclogite facies, and we published that in PNAS. And this is important because eclogite facies rocks are indicative of a cold subduction environment, and it's been argued for a long time that there are no eclogite facies mafic rocks in the Archean. Like, for instance, Bob Stern says no orogenic eclogites found in the Archean, but we think this is an orogenic eclogite facies rock formed in a cold subduction environment. So this was published 2 years ago in PNAS and has received a lot of attention. And this is the outcrop where the eclogite facies is from over here. If you go to this area, it looks like this. That's a picture I just showed over here. And the chemistry of these rocks is N-morb type composition, plotting over here. This is our detailed drone assisted mapping of the area, where it's a layered gabbro. There's a dark colored gabbro down here and a light colored leucogabbro on top. And these are the garnet pyroxenite layers in here, and part of the layered complex of this layered gabbro. So interesting, the gabbro has igneous ages of 2.53 to 2.52 billion years, and it has metamorphic rims on the zircons of 2.47 billion years, and a second metamorphic event at 1.82 billion years. And it's also cut by granitic dikes that are 2.47 billion years. And the hafnium isotopes suggest that it was derived from a depleted mantle source. So interestingly, the pressure temperature time path that we worked on over here with Jamie Connolly and others too, we have M1 deformation. The M2, the second metamorphic event, is the one that reached into eclogite facies, and then it's retrograded to a high pressure granulite after that. And this comes out to be 372 to 400 degrees Celsius per gigapascal, which is 11.2 to 12 degrees Celsius per kilometer, which puts it right here, right by the low temperature pressure facies series found in younger Archean in Cenozoic mountain belts like the Alps. For that, it should be around 10 degrees Celsius per kilometer to form way up in this area over here. So we're almost there. And we put that together with our PT estimates from further south in the Zanhuang complex, where we have high temperature in one area and the arc-related rocks, and we have colder, high pressure in the other area over here. So the Zanhuang complex, where its paired metamorphic relationship is found, is from this part of the North China Craton. So we have the cold rocks and the accretionary wedge, and the hot rocks over here from the R-type sequence. So we get two different PT paths from these different places. And this is part of the frontal part of the central orogenic belt that extends for 1,800 kilometers. And this was published by Wuhan as part of his PhD a few years ago, 2000. So to make a quick summary of that, we accreted these older arcs in the eastern block between 2.9 and 2.7 billion years old. And these are the approximate traces of these old sutures, 2.9 and 2.7. But this area is really poorly exposed. There's not many rocks here. It's the North China basin over here. So these arcs were accreted around between 2.7 and 2.56 billion years. And then the central orogenic belt was forming when the Wutai Fuping arc came in and merged with this to form the eastern block plus the COB. So we have this outward progressive growth of the Craton between 2.9 and 2.5 for this part of the Craton over here. And later we'll be talking about, if there's time, the reversal of subduction polarity over here at around 2.47 billion years old, and the accretion of these next terrains out here. So one question that we can ask is, how deep was subduction in the Archean? So we have all these indicators of collisions, accretionary orogenesis, and subduction. But how deep was it? So it might be that subduction was shallow, warm, and hot, and short-lived with lots of slab breakoffs, or maybe that it was very similar to today, and we had deep slabs penetrating to mantle transition zone or further. So as part of the way to solve this problem, we've looked at this part of the melange down here, and in here we have metasedimentary gneisses in yellow, banded iron formations with 2.5 to 4 billion years old age over here. But in this area over here, we have blocks of harzbrugite cut by dunite pods that have potiform chromites in them. So these look like this when we map in detail. This is from this area right here. This one is from this area over here. It doesn't matter anyway. But we have the harzbrugite over here, all subpentonized, and then we have these chromatite pods over here. Some of them look like this with this harzbrugite. Then there's dunite pod, and in the middle we have the chromites, and other ones are cross-cutting veins of chromatites. So the relationships to establish the age over here are pretty complicated. We have rhenium osmium ages of 2.55 and some older 2.7 on the chromatites. The peridiotites have lutetium hafnium ages of 2.53, and we have cross-cutting units like the granites of 2.47 and quartz veins of 2.48 billion years. So we're pretty sure that these are Archean structures. So the chromatites are really spectacular rocks. We have different textures. We have nodular, orbicular. We have massive chromatites. Some are cubic, but some of them have these really strange, bizarre shapes. And you can see they're full of inclusions. And some of these formed when the chromites were crystallizing and encapsulating whatever was there, either a melt or different crystal and rock fragments. And so they're preserving the conditions when the chromite was crystallizing at more than 1,000 degrees. So I'll go quickly through this. This is a really long paper published in Earth Science Reviews, but we have a very interesting array. Here we have a chromite inclusion and an olivine inclusion and a chromite grain included in melange, included in this origin in the world. So it's a bump on the back of a frog on a log type of story over here. But it's interesting because we put together what the melts and other stuff look like. The primary melt was more bonanitic when it formed. We have hydrous silicate inclusions like here, like hornblende. So there was water in the source. So it's probably a 4-arc type setting. And some of these inclusions are carbonaceous, like dolomites and other things that probably came from subduction of the older passive margin type sequence into depth. So we have this model here, where we have serpentinite and mud diapirs rising off of the subduction channel, getting mixed into with the mantle over here that is undergoing extension in the forearc. And so these melts are coming up through here and capturing some of these mineral inclusions that are being derived from the downgoing slab, plus ones from the normal mantle. And we have a bonanitic type melt in here. It starts to react with the harzligite to make the dunite and the chromites over here. So interestingly, one of the first indicators that these rocks have seen some ultra high pressures is this little part of this inclusion in here labeled 2. This is TiO2-2. It's an ultra high pressure phase of rutile that only forms, well, it forms at above 7.5 gigapascals at about 1,000 degrees, the crystallization temperature of chromite over here. So what we can say is that the material that formed this, the rutile and the carbonates and other things, were subducted to at least 270 kilometers and then brought back up when the serpentinite diapirs entered the mantle and the chromite-bearing melts were crystallizing in the forearc. So this is the model here. We have the older passive margin releasing the material to the forearc, coming up under extension over here, and forming these chromites like the TiO2, the ultra high pressure phase. And we've confirmed all this with lots of Raman spectroscopy and TEM imagery. So we're pretty sure about that, but I don't want to go into all the details in a short talk like this. But interestingly, at first, we took these rocks to GFZ in Germany. We were doing the work on the TEM there at the time. And we found that some of these white spots in here have a crystal structure that's not, it's chenmingite, which is the orthorhombic ultra high pressure phase of chromite. And this only forms at pressures greater than 14 gigapascals. So we're really excited when we found that. We weren't looking for that. So we went back to analyze it again, and it was gone. It's already retrograded. So we went, oh, so it's like ice cream on a hot day in Wuhan, just melts in your hand. But we have all the spectra. And then we kept on looking at this, and here's part of the PhD thesis of Hu Wei, who's going to graduate in a few months. And what he did is took more of these chromite samples from Zuling and these places over here and looked at them in detail. Here's the samples over here. And he was able to find that they have exsolution lamellae in them. Here's some of the backscattered image pointing to different exsolution lamellae. And you can see that they all have certain specific orientations. And it turns out that these are crystallographically preferred orientations of the chenmingite that they're exsolved along. The crystal is diopside because the low pressure phase of chrome cannot hold enough silica, so it has to exsolve when the pressure is being decreased. So this is further evidence that these were ultra high pressure phases that were incorporated somewhere after they formed by the mantle transition zone, 410 kilometers depth. So we think that these different things, the eclogite facies puts a depth constraint of around 65 or 70 kilometers. The TiO2 phase puts a depth of subduction around 270 kilometers. And the chenmingite puts a constraint on the depth to be around 410 kilometers, right at the mantle transition zone. So we think that this is placing some pretty good constraints on the possible depth of subduction in the Archean, at least the late Archean. So putting this together, we have different ways we can get ultra high pressure minerals into a subduction setting. One is they could be caught in a plume and rise through the mantle transition zone and be involved in the shallow convective system. Or we could have a subducting slab like this one here. This box is this figure, where we bring a lot of these crustal minerals down to the mantle transition zone. And if this next slab is rolling back, this is the Wutai Fuping arc over here. This is the older arcs accreted to the eastern block. When this is rolling back, it induces mantle flow in this direction. These arrows are a result of some of our numerical modeling. So the flow looks like this. So stuff that comes from below 410 kilometers to be entrained, and it would still be Chenmingite phase here. But by the time it's rising in the fork, it's dissolving to make the diopside exsolution lamella, and we have all of these trapped phases, the TiO2 and other things. So these are the ultra high pressure phase transitions that we can see. So again, to think about this on a more global scale, we have these different things going on the planet. Over here, we have the supercontinent cycles listed over here. We have the earliest microbiota on Earth around this age over here, around 3.8, maybe earlier life on Earth going back 4.4, 4.3 billion years. Traces of the origins of DNA go back, or RNA rather, go back that time. But these Zanhuang chromatites, just like the Zanhuang passive margin, are forming right about at the transition when the oxygen in the atmosphere went up by orders of magnitude, and we created a very different system of ocean, atmosphere, lithosphere interactions. So that's how we interpret the Eastern Bloc and the Central Orogenic belts after about 25 years of mapping, and many students work on their PhDs and masters and undergraduate theses. So we're supposed to only talk for about 45 minutes here. So I want to just quickly summarize what happens to the rest of the North China Craton. When did it become a craton, really? Because now we have this microcontinent forming, which is these different amalgamated arc systems, 2.51 in the green color, the COB. But out over here, we kept on adding these different elements until around 1.8 billion years. So to understand what happened next, we look at the arc continent collision going on in this area, the Banda or Sunda Arc colliding with the northwestern coast of Australia. So Timor is being thrust over the passive margin. This is the margin of the continent over here. And as that's happening, a subduction reversal, polarity reversal is happening along the Flores thrust, which is propagating to the west as the collision is ongoing. So likewise, after this 2.5 billion-year-old subduction system was shut down by this collision over here, we suggest, based on the structural geology of these accretionary rocks over here and intrusions, that there was a subduction polarity reversal event that happened around 2.5, 2.47 billion years. And that was starting to bring in these other terrains that are out here. So the next thing to come in is called the Ordos block, which is has very thick crust and very dense lower crust. And we think it has characteristics of oceanic plateaus by comparing it to other bodies like the Caspian Sea. And so we made this analogy that the next thing to come in was this oceanic plateau of the Ordos block, and that collided with the central orogenic belt and the already amalgamated eastern block of the Craton. So we're starting to add another thing, and this Ordos block is then heavily sedimented, and right now it's got many kilometers of Proterozoic, Paleoproterozoic, and to younger sediments on top of it. And then after that, we bring in the Yinshan ribbon microcontinent, which is another Archean basement block, but it has younger affinity arc sequences on top of it. So that came in. And the analogy would be that this is now the amalgamated Ordos block in the central orogenic belt and eastern block. And here's the Yinshan ribbon block in the Inner Mongolia North Ebal origin coming in. And it's similar in scale to the postulated Cordilleran ribbon continent. This is from Johnston 2008 paper over here. So we're saying it's a microcontinent that came in, and when that came in, the north margin of the Craton converted to an Andean margin. And so this is the map of the North China Craton at the same scale as the Andes. So this was a major time period between 2.1 and 2.3 billion years old of major magmatism, 2.3 to 1.88 billion year old magmatism going across mostly the northern half of the Craton, along with sedimentary basins forming that look like retroarc for them basins over here. And it's similar in scale to things like these basalts and things in the Andean forelands over here. So the next thing to happen was that the North China Craton was joining the Columbia Luna supercontinent at around 1.8 billion years. So for this, we look at an analog, which would be the India-Asia collision. And again, here's the North China Craton drawn on top of a map of Tibet for scale. So here's the different accreted terrains of Tibet over here. Here's a cross section. And here's a map showing the location of the 1.9 to 1.8, basically, billion-year-old granulite facies metamorphism. It's mostly concentrated in the northern half of the Craton, consistent with high pressures associated with crustal thickening like we see in Tibet today. And these are some of the younger post-orogenic granitoids. So our idea is that this is related to continent-continent collision at 1.8 billion years, with the Siberian part of the Craton, Siberian parts of the Columbia supercontinent coming in and colliding with North China Craton. So this is a scenario that's consistent with different plate reconstructions now, where the north margin of the Craton is the 1.8 billion year old origin. Some people, or a lot of people in China, used to think that this central orogenic belt, that they call the TINCO, Trans-North China Origin, was the 1.8 billion origin. But we suggest otherwise, that it's this north margin origin over here. And this would then correlate with these other Paleoproterozoic origins around here. If we look at the same thing on Zhengsheng Li's recent compilation of different supercontinents, this is his reconstruction at 1.8 billion years. We have North China Craton here, again, with the north margin origin being the 1.8 billion year old collisional suture. So what does this mean in terms of tectonic style? This is a paper that we recently published, again, with Bo Huang, who's a professor now, former students. So at 2.7 to 2.5, we envision that the North China Craton and other parts of Kenorland would have been sequences of oceanic arc sequences, oceanic plateaus that were amalgamating by around 2.5 billion years and forming larger protocontinents. And then by the time we have the Paleoproterozoic supercontinents, we have these collisions at 1.8 billion years, forming much thicker emergent continental crust. So we still have subduction, we still have plumes, so we have bottom up and we have top down types of tectonics. We might have had slightly warmer subduction. We might have had a lot more slab breakoff going on, according to some of the numerical models. But we definitely had subduction to the mantle transition zone. So that's very interesting to put this together. So a quick summary would be that we formed the North China Craton by accretionary orogenesis, starting at around 2.9 billion years. The major events around 2.5 billion years, forming the central orogenic belt, 1,800 kilometers long. And then 2.4, 2.3 additional sutures, and then the 1.9 to 1.85 billion year old suture when North China joined Columbia supercontinent. Okay, so in summary, we strongly favor this model for the main mechanism of craton formation, but we don't exclude the formation of mantle plumes and other things at different times and different places. So I think I kept to the time schedule. So I hope that I didn't go too fast and that somebody has some questions.
Great.
If you have questions, try to speak loudly because my speaker isn't working very well.
Okay, so we can switch to questions, and people can either raise a hand and ask question directly or type to the chat room. Okay, maybe I start with so you imply episodical collision, but from, I guess, late Archean to Proterozoic. But do you see evidence for passive continental margin between this
Do I see
collision?
evidence for what? I couldn't hear.
For passive continental margin deposition.
Yeah, so the section in the Zanhuang that I showed you, that resembles a passive margin, being that it goes from a high energy siliciclastic basal sequence, then it goes up into a carbonate sequence. But it's not associated with rifting before. It's not rifting an older continent and making a classic Wilson cycle type passive margin. So the idea, if I go back, is that after these arcs, these are the first ones that are colliding at 2.56 billion years. Here's one passive margin. After they collide, the crust is a little bit thickened, and the backside of this arc, the Qinghai arc over here, is what the passive margin-like sequence was developed on, and it's forming here from 2.58 to 2.51 billion years ago, before the next collision of the naps being thrust on top of it, as in this diagram here. So stratigraphically, it looks like a passive margin sequence, but it's missing the early rifting history. So this type of sedimentary sequence is like other ones that form like north of New Zealand, in that system over there. There's some carbonate type sequences on the backs of arcs. And the Altaides, we have similar type sequences forming during the formation and the accretion of multiple arc systems. They become stable before the next collision.
Kent Kondi has a question. Can go ahead.
You can't what?
Yeah, Tim, I think you made a superb case for Archean accretionary growth at 2.5. I don't think anybody doubts this anymore. What I was wondering is going back a little earlier on your map there to 2.7 and 2.9. Do you have any data at all that suggests that this sort of accretion would have started earlier, maybe at 2.9? Or could that still be some sort of a squishy lid or even a stable non-plate tectonic setting or somehow back there?
Yeah, for the 2.9 and 2.7 billion-year-old events, we do have stuff from the Shandong Peninsula down here relating to the ages of the 2.9 event. The 2.7 is a lot more clear. We have sutures coming through this area and up this area over here. We just had a paper, a group from Peking University and our group together on some of these microplates up in this area over here that they have different igneous histories before the 2.7 and different metamorphic histories, and they've come together along very highly deformed mélange belts. So that still looks accretionary at that time. But in the Eastern Hebei, where we documented the ultra-high pressure stuff, the eastern block of that is interpreted by some people, quite a few groups of some of our colleagues from Peking University and other places, interpret that as a squishy lid basin and dome pattern. And the reason is because it's mostly high temperature, very high temperature. The general outcrop pattern is fairly circular, okay? And the rocks, some of them have high pressures and some of them have low pressures. So they're interpreting that as dripping and coming back up in these buoyant diapirs. But for some of the work, we have a paper in review now, we're able to document that the circular structures are fold interference patterns from two different fold sets that are nearly perpendicular, making a classic fold interference pattern. And that is part of the same deformation events that we documented throughout the central orogenic belt. So it looks to me and our group that it's still a normal orogenic type deformation and not necessarily a squishy lid, but it is a different style in that part of the Eastern Bloc. So it's a very interesting ongoing question.
Thanks.
Thanks, Kent.
Paul, go ahead.
How does the Hutuo group fit into this picture?
The Hutuo group is over here in the, I didn't put a slide in of it, in south of Hengshan over here. So it's in this area over here. So the Hutuo group is Paleoproterozoic. And if I go back a little bit, it comes into this retroarc foreland basin over here in this age period. Okay. A long time ago, we thought it was Archean, and we thought it was part of this foreland basin from the collision, but the ages come out to be much younger now. So it's more likely part of this basin sequence. There's a review paper about that just published a few weeks ago. This one right here, Nature Communications, first author is Bo Huang, and we have updated information on the ages of Hutuo and these other Paleoproterozoic sedimentary sequences.
No, thanks, Tim.
Thanks, Bob. Good to see you.
Okay. Any other questions for Tim?
Tim, will you be in Wuhan in June?
Yes, I will. Are you coming to visit?
Yeah. Hope so.
Great. We can bring you to look at some of these rocks.
They should be undergoing high temperature metamorphism at that time.
Yeah. Well, June isn't too bad yet. Late July and August and September are the hottest times here. Yeah. So yeah, I'll be in contact and figure out how to get in touch when you're here. Maybe you want to see the Hutuo group.
Yep. Okay. Yeah, there are glacial deposits have been reported from it.
Okay, I was wondering if you were going to ask about the correlation in the age, because if we go back to, well, wherever that is, I have the different things going on, so it's in one of your glaciations.
Yeah.
But yeah, I haven't seen many people working on that here.
Yeah, of course, I heard about it a long time ago when it's thought to be Archean.
Well, welcome. I invite you to give a talk at COG.
Good.
Okay.
I'll be in touch.
Okay, great.
Okay. We still have a couple of questions, a couple minutes. So any more questions for Tim? Looks like maybe everyone convinced.
Most people in China are still sleeping. It's early morning here.
And I guess people here getting ready for dinner.
Yeah.
Okay, team. Looks like everyone is satisfied. So thanks a lot for your talk. And next week we switch to normal time and to different topic. So we will have a presentation about redox state of a mantle in Archean time, and if great oxidation event has anything to do with redox state of a mantle. Okay, so see you all next week. Thanks again, Tim.
Okay,
Good work,
thanks,
Tim.
Henry.
Keep
Everybody,
it going.
great. Thanks, Paul.
Thanks. Bye.